Let us next start the fourth section. In this section, we are going to see derivatives of trigonometric functions. Besides being mathematical curiosities, these derivatives are used in application as well. For example, in modeling periodic phenomena. You already know there are many important periodic phenomena in nature. Phenomena where the same thing happens again and again. For example, heart rhythms are periodic. The weather is periodic of our planet or elsewhere also. Many things are periodic. Atomic vibrations are periodic. So to model these things mathematically, we need derivatives of periodic functions. But periodic functions are not just these 6 trigonometric functions. There are others as well. So you may ask why we are using why we are focusing only on trigonometric functions. Why don't we more generally consider periodic functions and their derivatives? The answer lies in a result from advanced calculus, which tells us that any periodic function that we may ultimately end up using in modeling those phenomena is an algebraic combination of sine and cosine. So this makes the derivatives of these two functions in particular very important. Although eventually we will learn how to differentiate the other 4 as well, but first of all we are going to see how to differentiate sine and cosine. And for that we will need some special limits. That's why the section starts like this. And today we are going to see one theorem in that direction. So let's see what the theorem is. It states that if theta is measured in radians, then minus mod theta is less than or equal to sine theta, which is less than or equal to mod theta, and these same two numbers trap 1 minus cos theta between them. I have changed the inequalities slightly. In the book you will see strict inequalities, less than. I have allowed for equality here because I am considering 2 extra values, which the book doesn't really consider. There is one more thing. In the book, the statement doesn't say anything about what theta is. And you can see that here also. We are not saying for which theta. It seems like we are actually considering all real thetas. Well, I won't go into the details of what will happen if we consider all real values of theta. What will happen to these inequalities? Because we won't really need that kind of generality. So we are going to come to what theta is afterwards. Let us now instead see what the proof is, the proof that is given in the text, and then we will discuss about those extra values of theta. Okay, so this is the proof. The proof of course is geometrical because our definitions of trigonometric functions are geometric. So what do we have here? We have our usual x and y axis, and the angle theta has been put in the standard position. That is, its initial line coincides with the non-negative x axis and the final line is say here, OP. Along OP we have the terminal line or final line of the angle. So the angle is this much, that is theta. And the circle that you are seeing is a unit circle centered at the origin. So going back to what radian means, this means that the length of this circular arc AP will be theta. Why? Because by definition the radian measure of an angle is the length of the arc that it subtends divided by the radius of that circle in which the arc is a part. So because it is a unit circle, so radius, this OP is of length 1. So AP divided by 1 is theta. So AP is theta. This circular arc is of length theta. Okay, so theta equals the length of the circular arc AP. Now you concentrate on the right angled triangle. So you can understand we have joined O and P and A, where what is A? A is this point 1 comma 0. We have also drawn a perpendicular PQ from P on the x-axis. Now you concentrate on the right angled triangle APQ. Ideally we should have written AQP, but anyway APQ. Okay, so in this right angled triangle we can use the Pythagoras theorem. If we use that, we will get the sum of the squares of these two sides equal to the square of the hypotenuse AP, that is PQ square plus QS square equal to AP square. Now you note that whatever this circular arc is, its length is greater than the length of AP because it is curved, whereas AP is straight. Okay. So that is why AP square is less than theta square. Because and one more thing, this AP is actually the line segment AP, not circular arc AP. Okay. The circular arc AP has length theta, which is what you see here. This AP is the straight line segment length, which you find in Pythagoras theorem. Alright. Now, what are the lengths PQ and QA? Well, if you go back to the definitions of the trigonometric functions sine and cos, this angle theta has been put in the standard position, and this is the unit circle. So what should the coordinates of P be? Cos theta, comma sin theta. And by looking at where P is lying in the first quadrant. So cos theta means this length OQ is cos theta. Let me write here, OQ is cos theta and PQ is sin theta. Okay, it is weird to write from this direction, so you can see how bad the handwriting is, but anyway, you get the point. So now, OQ is cos theta, and what is the length of OA? 1, because it's one of the radii of the circle. So QA will be 1 minus OQ, that is 1 minus cos theta. That is why we have 1 minus cos theta here. And PQ is sin theta, that we are using directly here. Alright. Now what does this imply? It implies that, note one thing, the left hand side expression of this inequality is a sum, where both the terms are squares, that means they are both non-negative, and their sum is less than theta square. So obviously each one of them will individually be less than theta square as well, and that's how we have this. And then what we do, on both sides of these inequalities we take square root. But be careful, unless you know that the things which you are squaring are non-negative, you cannot just simply get rid of square and write that thing itself. So what I am saying here is that you cannot just simply write sin theta less than theta, because sin theta may be negative. We don't really know. Here sin theta is positive, but in general I am saying you have to use absolute value. I made a mistake here. We will need absolute value on both sides. Accordingly, from this second inequality also you have this. Now you can see that in place of this inequality you can write minus mod theta less than sin theta less than mod theta, and in place of this second one you can write minus mod theta less than 1 minus cos theta less than mod theta. So that is the proof. But note that the authors have already assumed that theta is greater than 0 and less than pi by 2. In the theorem statement, however, no such restriction is present, which means that this proof works only for that type of theta, which are positive and less than pi over 2 radian. What about other thetas? So that's where we are going next. So next we have this note. Let's see what the note says. The proof that you saw just now works for this type of thetas, that is those thetas that are greater than 0 and less than pi over 2. That is those thetas which when put in the standard position, their terminal lines lie in the first quadrant. And it's easy to see that these same claimed inequalities are also true for these two extra values of theta, 0 and pi over 2. And when you use these values of theta, you get equality actually. That is why I changed the inequalities slightly by allowing the possibility for equality. Let's see how. What do you get if you take theta equal to 0? This becomes 0, sine 0 is 0 and this is also 0. So yes, we have equality. And what happens to the second set of inequalities? This becomes 0. What is this? Cos 0 is 1. 1 minus 1 is again 0 and this is again 0. So for 0, both the inequalities are true. Both sets of inequalities are true. What happens when pi over 2 is taken? You get minus pi divided by 2 less than or equal to sine pi divided by 2. Less than or equal to pi divided by 2. Sine pi over 2 is 1. Essentially, if you go back to the inequalities that come before this, that is which tells us that mod sine theta is less than or equal to mod theta. There if you put theta equal to pi over 2, you get 1 less than or equal to pi over 2. Is it true? Yes, because pi is 3.14159 something, which if you divide by 2, you will get 1 point something. So it's a little larger than 1. But anyway, you have inequality. What do you get in the second set of inequalities when you take theta equal to pi over 2? Again you get 1, because 1 minus cos pi over 2 is 1, cos pi over 2 is 0. So this is also true. But say you want to have the same inequalities for negative thetas. Not all negative thetas, but say this type of thetas which are negative but greater than minus pi over 2. Will they still be true? Let's see. If you take a theta like this, then theta satisfies these inequalities. Now you multiply throughout by minus 1. So the inequalities change direction. And ultimately you get 0 less than minus theta less than pi over 2. So minus theta is an angle like this. So you can apply the inequalities with minus theta in place of theta. Say I do that. Okay, minus mod minus theta, all these things I do. We can see minus mod minus theta, here sine of minus theta, here mod minus theta. And here also in the second set of inequalities, all the thetas have been replaced by minus theta. Now the minuses inside modulus simply vanish because it's absolute value. So you get minus mod sine, minus mod theta less than or equal to, but sine minus theta is minus sine theta, which is less than or equal to, where is it? This, which is mod theta here. And the second set of inequalities just immediately reduces to what we need, because the minuses vanish here and here because absolute value is there, and cos minus theta is cos theta. So there we actually have what we want to have. What happens to this though? This first set of inequalities you multiply throughout by minus 1 again. So that will give you, actually we have started writing from this side because the inequalities change direction. So, well, no, that's not what we did actually. We kept the positions of the terms intact and we changed the direction of inequality. So this becomes plus mod theta, greater than or equal to minus of minus sine theta is sine theta, which is greater than or equal to minus mod theta. So you ultimately get back same inequalities. So even for negative thetas like this, we have our inequalities intact. If you want, you can include minus pi over 2 also, but that won't be necessary. Now, why are these thetas only sufficient for us? See, the thing is that we are ultimately going to investigate some limits as theta tends to 0. So we don't really want theta to approach 0 only from the right side. We want it to approach 0 from the left side as well. That is why we needed this slight extension of the result, which means that we can now understand or accept that whatever theorem 3 tells us, it works, those inequalities work for theta lying between minus pi over 2 and pi over 2. Okay, that will be enough for us. As a simple application of that theorem, next we have this example where we have been asked to show that the functions sine theta and cos theta as functions of theta are continuous at theta equal to 0. Remember, when we first introduced these functions, at that time, well, actually when studying continuity, we simply stated that these functions are continuous and we accepted that without any further question. So now we can prove it. What does sine theta, for example, being continuous at theta equal to 0 mean? It means that if you calculate this limit, it should be equal to the value of sine theta when theta equal to 0, and that value is 0. So if you can show this limit, that means sine theta is continuous at theta equal to 0. Similarly, for cos theta to be continuous at theta equal to 0, this limit should be equal to cos 0, which is 1. So let's now see how we can use that theorem to prove these limits. So this is the solution. As theta tends to 0, both mod theta and minus mod theta approach 0. They also both go towards 0. And both the functions sine theta and 1 minus cos theta are trapped between those two functions. So this is the perfect situation where you can use the sandwich theorem, which if you do, the theorem immediately gives you these two limits. The trapped functions also have to approach 0, that same common limit as the trapping functions approach. So this is one of the limits. For the other limit, you apply algebra of limits here, because the constant function 1 approaches the limit 1 regardless of where theta goes. So I won't say anything more than that. Okay, from that it follows that the limit of cos theta as theta tends to 0 is 1. Okay, so that way you have this fact. And in the next video on this, we are going to see this limit. We are going to prove this limit. Equals 1. This is a very important limit which is used in many places. I have heard that it has some kind of use in electrical engineering. I don't know, I mean, this is something I have heard. And finally, do you notice one more thing? In order to fully consider this limit, we are actually considering theta approaching 0 from the right side as well as from the left side. However, the proof that the original theorem gives us, that is the text proof, only considers positive theta. So we really need negative theta. We have, however, arranged for that. Okay, so now it is complete. We really have these things and we have these inequalities also. So that will be all for tonight. So see you tomorrow with a new upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.